Okay, in the next video, we're going to talk about the regression fallacy. But before we do, I thought it would be a good idea to sort of pause and review some of the main points that we've learned about correlation and the SD line and regression, in the regression line. And I wanted to do this because I know when I first learned all of this, it was really confusing to me. And so I've got a feeling that if you're going through this playlist, then you've probably got a bunch of unanswered questions all over the place, or at least a bunch of things that you don't feel are as clear as you'd like them to be. So, okay, correlation, or the correlation coefficient, we know that there's different ways you can describe what the correlation coefficient means. One of the ways is that it's a measure of the degree to which a set of data points, you can think about it on a scatter plot, are clustering around a line. So the data points on a scatter plot is meaning that you have a relation between two variables. An independent variable, which we typically put on the horizontal axis, x, and a dependent variable, y. It's these two lists of numbers, and so each pair of numbers from x and y are related, so you can plot all of the points on a scatter plot. And the correlation coefficient is giving you a measure of the degree to which these data points are clustered around a line. Okay, but now what line are we talking about? Because there's really two lines we've been studying. We have the standard deviation line, the SD line, and the regression line. So what line is the correlation coefficient referring to? It's referring to the standard deviation line. So we know that you can draw an outline around the data points of a scatter plot to kind of give a summary of that scatter plot. So we could erase these data points and replace them with like an outline like this. So like you could think about, we could erase the data points and just have a general sense of the distribution of the points with this outline here. Well, okay, the SD line, if you think about this as like an ellipse, the SD line would be the major axis of the ellipse. It runs right down the center of the data. It's like a line of symmetry for the data points. And so that's why that's what the correlation coefficient is. That's the line that the correlation coefficient is referring to. All right, now, but what's a little bit confusing about this is that we know that the regression line, so the whole purpose of regression is we want to see how the dependent variable y depends on x. What that means is that if we're given an x, or we just like input an x, we want to, as accurately as possible, predict y. So it's like if this was some heights versus weights, if we brought in a height of like some new person, let's say, some new person into the data set, so we know the height and we want to predict what that person's weight is based on the existing data we have. So like this is heights and weights. Okay, well, we would think that if we're going to have a line that's going to map the dependence of W on H, we would think it would be the SD line. It goes right down the center of the data. This would be our best, if we have a height, our best predictor would be, take that height value we have and go to this line and get the weight. But that turns out to not be the case. So both the SD line and the regression line go through the point of averages of the data. That's the point that corresponds to the like H average and W average, the average of the heights and the average of the weights. So both lines are going to go through the point of averages. But the regression line is always going to be, it's never going to be as steeply inclined as the SD line. At best, it'll have the same inclination. They'll be the same line. But it's always going to be shallower or not as steeply inclined as the SD line. Okay, so that's interesting. Why is that the case? Well, we'll come back to that in a second, but let's first think about how, so the correlation coefficient, we know that like the classic correlation coefficient, it's a linear correlation coefficient. It's telling you the degree to which the data is clustered around the SD line. Okay, but we talked about how this coefficient isn't universal, that there could be cases where the data is nonlinear. So you could have something like this. In this case, this data would not be appropriate to apply the classic linear correlation coefficient. You want to apply some sort of nonlinear correlation coefficient for this data. And so one of the things that we talked about was that it would be interesting if you would make some sort of a Python or MATLAB code that could take in some scatter plot data and then run it through a bunch of different correlation coefficients related to, like, okay, the linear correlation coefficient, but then a quadratic one, or any kind of even or odd order polynomial, a square root, cube root correlation coefficient, a exponential, logarithmic. And you get these lists of correlation coefficients related to basic function types, and then you pick out the highest 2 or 3 and disregard the other ones. That's one way of figuring out what the correlation of a set of data is, of a relationship between two variables. You could take the highest 3 correlations, and maybe those correspond to exponential and quadratic. And so then you could come up with some general function that it's got some exponential character, but then it also it incorporates quadratic as well. Just find these coefficients. Okay, but what we've learned, though, as we've continued through these sections, is that it's not necessarily the case that if you had a linear correlation coefficient of 0.1, so that's really low, or like negative 0.1, that's pretty low. Okay, well, that does not necessarily mean that this correlation coefficient doesn't apply to your data. This still might be the perfect correlation coefficient for your data. So how does that work? Well, something else that you're going to want to analyze, that you want to incorporate into your code, is you would want to do an outline of the data. So the outline here would be something like this. Okay, and if you saw an outline like this, then it doesn't matter what the linear correlation coefficient comes out to be. If it somehow in this case, there's a vertical symmetry, so it will come out low, but maybe for some reason it still comes out high. A linear correlation coefficient might come out high for something like this, right? You would get, okay, but that doesn't mean that even though it's high, it doesn't mean that the linear correlation coefficient applies. When you look at the outline, okay, a linear correlation coefficient is going to apply if you've got if the outline is elliptical or circular. So if you've got any kind of elliptical outline, or even like a nice circular outline, which would have no correlation with the linear correlation coefficient, this data is still perfectly applicable for the linear correlation coefficient. Yeah, the correlation is going to be 0, but that's correct though. That the linear correlation coefficient is telling you that there is no correlation with that data. So that's something else to think about when it comes to finding with the correlation coefficient. You're not just looking for the degree of correlation, but also the degree of non-correlation. So you're really looking for the most. It's not about finding the highest correlation coefficient. It's really more about finding which type of correlation coefficient is most applicable for your data, and then whatever the correlation coefficient is, that's what it is. Okay, but now, why is the SD line? So here you can see that outline would be elliptical shaped. And there's the SD line. Why isn't the SD line the perfect line to use for the purposes of regression, for the purposes of predicting y on x? Well, the reason is because the SD line is not a function of the correlation coefficient at all. It doesn't take into account the degree of correlation at all. So again, the degree of clustering around the SD line is not taken into account whatsoever. That's the reason why the SD line isn't appropriate for all circumstances. Unless it's a perfect correlation, 1 or -1, you don't want to use you want to use some other line for the purposes of regression. Okay, well, once again, regression being it's the task of you're trying to come up with the equation of a line, or there could be nonlinear regression as well, so the equation of a quadratic, etc., that shows you how y depends on x, or how the independent variable depends on the dependent variable. Meaning, if we bring in another father-son pair, a new father-son pair, and we know the height of the father is 66 inches, okay, we want to predict as accurately as we can what the height of the son would be. That's regression. Well, okay, I take that back. That's technically curve fitting. That's curve fitting, and there's different methods of curve fitting outside of regression, but regression is where you're either directly or indirectly making use of the correlation coefficient, or the degree of correlation of the data, to come up with the curve fit. Okay, so how do we use that correlation coefficient? Well, okay, if the father's height, that this new data point comes in, and the father's height is 66 inches, okay, well, all right, we would come to the SD line, right? That would be initially what we would think we should do. Well, okay, if there was a perfect correlation, that's fine. But because this data is scattered around the SD line, then you can see that's not going to work. Look, we're way too low here. We want to, when it comes to regression or curve fitting, the optimal answer to what would you predict the output to be based on the input would be, so you make like a little small interval around 66 here, so you have a bunch of data points within this input window. Well, we want to pick the average of all of the son's height values. The average of all these values, which would be, looks like all these values somewhere right in here. That's the guess we want to make. There's no other right answer to that. In any circumstance, that would be your best guess for making a prediction on what some new data point is going to be. You have all these fathers that have a height of right around 66 inches. All these fathers, all these data points. Well, what was the average, as long as there's no other kind of, all things being equal, well, what's the average son's height with all those values? Again, assuming there's no extraneous confounding variables, what's the average? Well, that's going to be your best guess for the next one. You can't get a better guess than that. So that's the goal of any kind of curve fitting method. That's what you're trying to predict. Okay, and so look what the SD line would predict. That's not right, and the reason is because it's not taking into account the correlation coefficient, which tells you how scattered the data is about the SD line. Okay, and so how do we incorporate the correlation coefficient to make a better prediction than this? Okay, well, so the SD line, the definition of the SD line is we've got the point of averages somewhere that corresponds to the average father's height and the average son's height. It's the coordinates of x average, y average. Okay, and so the SD line and the regression line are both going to go through this point. Now, the slope of the SD line is just going to be the standard deviation in the y direction divided by the standard deviation in the x direction. And now, but because standard deviations can't be negative, then you just need to, if the correlation of the data is negative, if the cloud is downward sloping, you're just going to manually put a negative in here. If it's positively sloping, you just leave off the negative. Okay, so you can see there's no correlation coefficient in here whatsoever. Okay, Now, the regression line, we have a point and a slope. A point and a slope is all you need to define a line. The regression line, we have a point, right? The point of averages. But what's the slope? All you're going to do is, instead of here, if you want a certain number of standard deviations in the x direction from the point of averages, then you go that same number of standard deviations in the y direction to get to the SD line. If this is one standard deviation in the x direction, well, then this is going to be one standard deviation in the y direction to get to the SD line. All you're going to do is, when it comes to the regression line, you're just going to say, okay, you go a certain amount in the x direction, and then the amount that you're vertically going to move is r sigma y. That's it. Now here, the r is going to take care of if you have a negatively sloped or positively sloped line, so you don't have to like manually add a negative. But that's it. That's it. And so what this is going to do is, if we had a father's height that was around 66 inches, okay, so we move a certain number of standard deviations in the x direction. This would be negative because you're below the average, okay? So let's say this was a half of a standard deviation. Okay, well then we figure out what a half of a standard deviation in the y direction is, and we multiply that by the correlation coefficient. Let's say the correlation coefficient is 0.4. And so when it came to the SD line, we would go all the way down to the SD line, a full sigma y. Well, now we're just going to go a portion, like 0.4 of that, like right there. You see? So the scattering, the degree of scattering is being factored in here. You see how the regression line, but with the incorporation of the correlation coefficient, factors in the degree of scattering. And that's it. That's it. This is the fundamental classic linear regression method. It's that simple. Just taking this R and applying it to the SD line slope, but you include the correlation coefficient. This is the fundamental linear regression method, where you're going to have some football-shaped, elliptical-shaped cloud. Otherwise, you wouldn't be doing linear regression. Okay, and again, you're just adding in the correlation coefficient as a multiplier to the SD line slope. Okay, now that's fine, but why are there multiple regression methods? Isn't there like least squares regression, like linear least squares? I mean, we're done, right? Because now we're going through all of the different points of averages. This is at the 66 inch. That's the point, the average of all these data points. And if we just follow this, we have a line now, right? We have a point, the point of averages, and a slope. So the line is fixed. There's the regression line. Here's SD. Here's regression. So we're done. I mean, right? This is going to be if we drew here, right around 72 inches, the regression line is going to be the average of all the points within this column here, all these points. Well, actually, it doesn't work out that way. If that was the case, then yes, there would be no need. If that was always the case, then there would be no need for any other regression method. But it doesn't work out that way. You can kind of see here, it looks like this average is a little bit low. It's better than the SD line. It looks like the average might be here. Okay, and so if we take a look, here is a graph of averages and a regression line. So if you drew a column around x is equal to 73, what they're saying is that there would be 37 data points all throughout this column, and this is the exact point of averages, at least as far as the weights, the y direction, because the x direction average is 73, of all those 37 data points. So look at where the actual points of averages are. They don't all line up on a line, unless that's like a special case of it's actually perfectly correlated. So in general, all these points of averages aren't all collinear. And that's why there's multiple regression methods, because like least squares says that, okay, I think I can come up with a better way of mapping out these points of averages. It's going to kind of run down the center of these points better than the regression line. And so, but how does like least squares work? So that uses I mentioned that regression meant that you're using the correlation coefficient either directly or indirectly. But like regression isn't a universal term for curve fitting. There's other curve fitting methods outside of regression that try and find the best curve fit, linear curve fit to all these points. So outside of regression, that would be like machine learning algorithms or like Fourier transform. But regression is you're applying the correlation coefficient, either directly or indirectly. And that's what like linear least squares is doing. It's not a simple just bring in the R coefficient and it's like a simple use of it like the classic regression method. It's kind of using it in a roundabout way. Whenever we go through least squares, we're not going to be directly using the correlation coefficient, but it's still tied to the correlation coefficient. It's still kind of, you're using that degree of scattering. You're taking the sum of the squares, the RMS of all of these vertical distances from the best curve fit line. So it still is kind of incorporating the degree of scattering indirectly. So it's called regression. Well, actually, some people they like to say it's not regression. So you'll hear both. Okay, now, but again, as I mentioned, you can see why the regression line is always going to be less steeply sloped than the SD line, because the slope of the SD line is sigma y over sigma x. That's the magnitude. It could be negative if you apply the negative, but that's the magnitude. The slope of the regression line is r sigma y over sigma x. Well, the magnitude of r is at most 1. It's always going to be less than 1. So you could have a regression line that's equal to the SD line if r is 1 or negative 1, but outside of that, it's going to be more shallow sloping. So if we're asked here, which line is the SD line, which line is the regression line? Well, we know this has to be regression. This has to be SD. This has to be regression. This has to be SD. This has to be regression. This has to be SD. This has to be SD. This has to be regression. For the linear case, this is for the linear case, for a football-shaped cloud, or circular, elliptical-shaped cloud, or circular-shaped cloud. This looks almost circular. That's why the SD or the regression line is almost flat. There is almost no correlation. R is almost 0. But now that don't let that confuse you. That doesn't mean that just because a regression line has a shallow slope means that the correlation coefficient is low, because you could have something like this, and that would have a really high correlation coefficient. So what's the difference? The difference is for the R, the low R, you're moving a certain amount in the X. Okay, a certain number of standard deviations in the X. Okay, but because the data is so scattered, then the R is saying, well, look, we're not going to be going up a full standard deviation in the Y. We're going to be going just barely moving up at all, because it's so scattered. There's like no correlation. So it's just it's way spread out from the SD line. Okay, but if you had a high correlation with a flat with flat data, well then, okay, you're going to have this sigma y over sigma x with the R. So you move a certain amount in the sigma x, right? But the sigma y is going to be low as it is. So you're going to have R as 0.97. It's going to multiply by a sigma y that's already low to begin with. So it's still correlated really well. It's just that sigma y itself happens to be low. Okay, and now we also talked about how if you're comparing ranks of an input data point to an output data point, when it comes to linear regression, then unless you have a perfect positive 1 or negative 1 correlation, then you're always going to see if someone had a high rank coming in. So like we can think about a rank being, if this is like a test score, if you were in the upper percentile, so above average coming in on like the input test score, whatever it would be, then on average, your output test score is going to, at least your percentile rank is going to drop. Your percentile rank, not the test score itself, the rank. So if you came in and you were in the 90th percentile of father's heights, meaning you were taller than 90% of the data points for father's heights, then on average that we would expect that the son's height is going to be a lower percentile rank. So if you're in the 90th percentile of father's heights, then the corresponding son's height would be something like the 70th percentile. You're taller than 70% of all the sons. But on the flip side, if you're in the below average case, if you came in and you were a father that was in the 30th percentile, so only taller than 30% of the data points, then we would expect your son's height on average to be the percentile rank comparison to son's heights would be like 45%. And we talked about this a little bit, but where this is coming from, which we didn't talk about yet, is it comes from the regression fallacy. That this is something that's uniquely related to linear correlations, linear data. So these football-shaped clouds where you can, it's not necessarily linear. It's just any kind of, because like if R is 0.2, that's not really that linear, but it still applies to the linear correlation coefficient. With this kind of data, this is where we see the regression fallacy come from. And so in this upcoming section, we'll talk about the regression fallacy and then come back to percentiles and see how it relates to percentiles. So in this next video, when we talk about the regression fallacy, we'll at the same time talk about how this relates to the fact that the percentile rank always goes down if you're above average from the input to the output, and always goes up, or on average always goes up if you're below average coming in.